Hello everyone, welcome to lecture 31 of the online course Modern Display Technologies Flat Panel Display. Today's lecture will be on active matrix displays. Here is the lecture outline. We'll first discuss why we moved from the passive to active matrix addressing, and then we'll look into the active matrix, that is the TFT LCD device structure. We'll go into the details of TFT structure and its operation, and see the methods of holding the voltage and balancing DC, and also towards the multiplexibility, something like the Rhodes and the bistable LCDs or liquid crystals. So here we'll basically try to bridge limitations of the passive matrix methods, okay, and we will see that how we derive the active matrix addressing. So let me remind all of you of the punchline numbers that we got from the previous lecture. Was that in the standard twisted pneumatic passive matrices, they are basically limited to roughly 9 well addressed rows, okay, and this is a consequence of the crosstalk fundamentally growing with the number of rows. So you basically want to maximum go up to n equals 9 for twisted pneumatic LCDs to keep the crosstalks minimum, okay. Now the core problem here is that every pixel is basically influenced by voltages which are meant for the other pixels. Thereby there is no way to actually electrically isolate one pixel from the rest of its row or columns, and that basically brings this active matrix solution, okay. So what is this active matrix? Here you basically give every single pixel its own electronic switch, that is in terms of a transistor, it's a thin film transistor or TFT. So its voltage can be set and then held independent of what's happening elsewhere in this particular matrix. So this is the subject of this particular lecture today. We'll be talking about that active matrix addressing, which is the dominant technology behind essentially all modern laptop, monitor, phone and TV LCD panels. So this is the schematic of the device structure of a TFT LCD color pixel, okay. So active matrix displays, they basically use thin film transistors as electrical switches to control each pixel's transmissive state, so it can offer excellent image quality, and these are standard for the direct view displays. Now since these liquid crystal layers do not emit light, so you basically require a backlight and a diffuser to basically homogenize it. So this is how the structure looks like. So you have this backlight and then a diffuser that basically homogenize this incoming light from the backlight, okay. Now high contrast needs linearly polarized light, so you basically use 2 sheets of stressed dichroic polarizers that basically sandwich the cell. So you can see here there is basically one polarizer over here, okay, and then you have another polarizer over here. So you are basically sandwiching the liquid crystal cell between the polarizers, okay. Now look carefully, this is basically the TFT substrate. So you basically require one glass substrate that basically hold this TFT array, which are basically the light switches which are basically marked here, amorphous silicon TFTs, okay. So you can see that you are able to control each pixel independently, which can be controlled by this TFTs. So the typical cell gap, so this is the place for the liquid crystals, okay, and then on the other side you have this common electrode, okay. So this one can be considered as a gate or a row electrode. Okay, so between this gate or row electrode and on the other side you have this common electrode which is shown here, after which you have a color filter and then a common substrate and a polarizer, right? So these are the typical dimensions of each pixel, and this is the height of the overall cell. Okay, so the typical cell gap here for the transmissive LCDs is around 4 micrometer. Okay, and the display performance such as throughput, response time, viewing angle, etc. will be set by the liquid crystal mode that is being used in this particular pixel. So now each display subpixel, as you have seen, is basically controlled independently by its own TFT, which is positioned at the corner of the pixel. Okay, and typically amorphous silicon, that is a silicon, okay, like this, or alpha silicon people write. So these are the standard TFT material, which is also photosensitive, so it must be shielded from both the backlight, so that is done using the gate metal lines, and you also need to shield it from the ambient light, that is achieved using the black matrix. Okay, now the aperture ratio is basically the fraction of the pixel area that is transparent. Okay, and that's basically the active ITO electrode, which you can see here. Okay, these are the active ITO electrode, and on the corner you have this alpha silicon TFTs. Okay, so this active ITO electrode area is basically the light transmitting area. Now, because you actually put some sort of opaque TFTs on that area, and some regions are black matrix region to shield the TFTs from light. Okay, so your aperture area basically drops to roughly 80%. Okay, there's a typo here maybe. Okay, so it can drop to roughly 80 to, it can go to almost 0% depending on the device resolution and the panel size. So higher resolution means relatively more area is lost to the TFTs and black matrices, and that will give you lower aperture ratio. Now we have also seen another component here, which is the color filter. Okay, so what is the role of the color filter? So for direct view displays such as notebooks, desktop monitors, okay, compact size and lightweight matters. So you basically want to have the color filters typically embedded on the inner side of the second substrate. Okay, that is where you have basically put the color filter. So each color filter is built from 3 pixels, that is R, G and B. Okay, so each subpixel's color filter basically transmits its own color and it will absorb the other 2. Okay, so any single color filter alone can transmit less than 33% of the incident light, 1/3, right? So what are these color filters? These are basically pigment based materials which typically have 80 to 85% transmittance within their own color band. So overall you can say that the net transmittance of a single color filter is roughly around 27%. So this is roughly 1/3 of the light times the pigment's own transmittance, which is basically 80 to 85%. So roughly you get 27% of the light out of a single color filter. Let us see how we calculate the overall optical efficiency. Okay, so if you combine all the different loss mechanisms that has been covered till now, which involves 2 cross polarizer, and then you have this color filter which have individually 87% transmittance, and also you have this TFT aperture ratio which allows 80 to even 0%. So altogether these are all different loss mechanism. So if you put everything together in place, you will see that the overall system optical efficiency for a direct view LCD panel is only about 6 to 7%. So to improve such, or you can say with such low optical efficiency, still you need some good amount of light to come out. So how you can compensate this? You can basically make the backlight brighter. So your backlight must be driven much brighter to compensate. So that will essentially consume more power for your entire device. So if you consider any portable or battery powered display, what you prefer is the low power consumption one, right? Because that will directly extend your battery life. But this is not helping you, right? Because you need to drive it with higher power so that you get good amount of light out of this display. So for LCD TVs which are plugged into main power, okay, their power consumption has historically mattered less, even though it is increasingly addressed for energy efficiency reasons. So you can understand that the power is not a problem if it is directly plugged into the main power line, okay, but then the energy efficiency is always a problem with this kind of LCD TVs, because only 6 to 7% optical efficiency is what you are getting. Now we have also seen that amorphous silicon TFTs are basically preferred for large screen direct view LCDs, but they have simpler manufacturing process which is good and lower cost as compared to the polysilicon ones, okay, or the P silicon. So let us look into the comparison between the two in this particular aspect. Another important parameter that comes into consideration is that the amorphous silicon's electron mobility is roughly 2 orders of magnitude lower than that of polysilicon. That means 100 times lower than that of polysilicon. And how does lower mobility affect? So for lower mobility, every alpha or amorphous silicon TFTs basically needs larger pixel area to maintain adequate amount of charge storage. So that is basically limiting the achievable resolution, because the TFT size or the pixel area is larger, okay. So typically you can see that amorphous silicon subpixel size is typically 80 by 240 micron. So if you take 3 subpixels for R, G and B, that will combine to a 240 by 240 micrometer for one color pixel, okay. On the other hand, the polysilicon has much higher electron mobility, so it is possible to have much smaller pixel size, so that can lead to higher device resolution, okay. So especially these are valuable for small screen LCDs, okay, like where you have a high PPI, okay, where the aperture ratio is critically the concern. So here we'll see the most common TFT architecture in the inverse staggered or bottom gate type. So this is the bottom gate TFT structure. So here S stands for source, G for gate, D for drain, okay, and this BM is the black matrix and CF is basically the color filter. So this is where you have the backlight, okay. So you can see the light from the backlight is basically this patch portion, the light is not able to come out because this is blocked by the TFT. On the top side also you basically put a black matrix so that ambient light cannot disturb this TFT because these are photosensitive, okay. So only these two layers between the ITOs, these are the liquid crystal, through the color filter, this is where the light is coming out, and you can see the transmission is weak, okay. So here the ohmic layer, which is N plus amorphous silicon, is the channel region, okay, and that can be formed either by direct etching or by etching through a protective film. Each approach will have its own trade-off. Now, what is the advantage of having this bottom gate structure is that it is relatively easy to fabricate, okay, and it has 30% higher electron mobility as compared to the top gate staggered type kind of structure, okay. So these advantages basically make the bottom gate structure more favored TFT structure for this kind of TFT LCD applications. Now, as I already mentioned that your amorphous silicon is basically, this is the amorphous silicon layer, okay. So amorphous silicon layer is already photosensitive, so it must be protected from both the incident backlight, okay, and also from the ambient light, okay, especially when you are driving this backlight high, so your backlight intensity is very high, so you need to protect it from there, okay. So how do you do that? Actually, the amorphous silicon itself should be kept as thin as possible, so that will basically minimize the photo-induced current. Otherwise, it may degrade the signal to noise ratio of the stored pixel voltage, because it can produce some extra current based on the light that is getting exposed on this alpha silicon or amorphous silicon layer, okay. Now, in the bottom gate structure, you basically have this opaque gate electrode that is formed directly at the TFT channel region. So this basically also works as a light shield layer that protects against the backlight that is coming from this bottom side, okay. And on the color filter substrate, that is the one on the top, there you basically apply a black matrix that shields the TFT from the ambient light which is incidenting from the above. So always note that in reality the actual device is not up to the scale. So here it looks like almost 50% or at least 40%. It's not like that. The TFT and the black matrix regions are much smaller relative to the transparent areas of the ITO, okay, which is shown. It is not exactly like this. So with that understanding, here you can see the equivalent circuit of a single pixel of TFT LCD, okay. So this is the TFT, this is the gate, this is the data bus line, okay. This part is the source and this is the drain. So here you have this pixel electrode which is ITO, you have the color filter, you have the common electrode again made of ITO, then you have the black matrix here. So here you will see you get some sort of storage capacitor CS, and then here you have the liquid crystal capacitance CLC, okay. So once the gate voltage exceeds a threshold, you will see that the TFT switch basically opens, that means it conducts. So in that case what happens, the source data voltage is then transferred to the drain, so which basically connects the bottom pixel electrode, right. So now the bottom pixel electrode together with the gate line, that basically forms a storage capacitor which is modeled as CS, and that is basically critical for holding the pixel voltage after TFT switches off, okay. So you can basically see the equivalent circuit model here as well. This is the data bus line and this is your pixel electrode and this is your TFT, and you have this CS capacitor that holds that one, and this is the liquid crystal capacitance, okay. So if the resulting voltage across the liquid crystal layer exceeds the liquid crystal threshold voltage, in that case the liquid crystal director will reorient and it will start modulating the backlight. Now the detailed transmission characteristics basically depend on the mode of the liquid crystal which is being used. So normally white will be the case for twisted pneumatic, or normally black for in-plane switching or multi-domain vertical alignment or VA modes, okay. but in both of these cases the polarizers are crossed, so only the liquid crystal's field dependent optical state will vary. What we also see that DC voltage would cause undesirable electrochemical degradation of the organic liquid crystal molecules, and that is why DC voltage is avoided, and for that matter passive matrix AC drive discussion was done in the previous lecture. So what happens, the polarity of the drive voltage is basically alternated every other. So what is the typical gate operation? So plus 20 volt is used for the switch on state and minus 5 volt for the switch off state. Okay, and under these conditions a amorphous silicon TFT basically achieves an on off current ratio which is greater than 10⁶. That means the switch is extremely clean and it strongly conducts when it is on, and it strongly cuts off when it is basically off. So here we will look into this example of tracing through 1 pixel's voltage. Okay, so let us set up this scenario. The common ITO electrode that you see here is basically the common ITO electrode that is placed on the color filter substrate is held at a fixed bias of plus 5 volts. Okay, and for a particular grayscale level we want to write, okay, the data line basically carries plus 8 volts. Okay, now let me walk through the switching event. So when the gate voltage on this pixels row exceeds the TFT's threshold, the transistor basically turns on. So in that case the current flows from the source through the channel to the drain, and this basically charges up the storage capacitor CS to match the data voltage, right? So since this drain terminal is directly connected to the bottom pixel electrode, that is the one facing the liquid crystal layer, you can see the drain voltage of plus 8, okay, appears there, right? Now if you are computing the effective liquid crystal voltage, since the top electrode basically sits at plus, the top common electrode sits at the plus 5 volts and the bottom pixel electrode sits at plus 8 volts, so the net voltage that is being applied across the liquid crystal layer is basically the difference of these two, so you are basically having plus 3 volts. So this is the voltage that is exactly driving the liquid crystal director reorientation for this grayscale level. Okay, so that you can actually see. So this is how the movement occurs. Okay, so if the gate voltage, so initially, so the charge is applied, okay, this gets charged up, you get 5 volts here, the effective voltage across the liquid crystal layer is 3 volts, that we understand. Okay, now if the gate voltage is then removed, okay, or it drops below the threshold, in that case the TFT basically turns off for the rest of the frame time. So that is typically 16.7 millisecond at 60 Hertz frame rate. So here it was 27 for the odd frames. Okay, so during this method what happens, the storage capacitor CS holds its charge and the pixel voltage level remains at plus 3 volt that you see here. Now to balance DC over time, okay, so that you can actually avoid the electrochemical degradation, so you can see in the next frame that reduces the data voltage to plus 2 volts. Instead of plus 8 it goes to plus 2. So in that case what happens, the TFT again turn on, okay, and in this case the drain voltage is plus 2, because here it is plus 5 the common voltage and here it is 3, so 2, so the difference is minus 3 across the liquid crystal layer. Okay, so the drain voltage of plus 2 is basically giving the opposite polarity, okay, that you see here, and the same thing remains here as well. Okay, so what you understand is that why this DC bias is dangerous. It's mainly because of the ion migration. The liquid crystal's reorientation dynamics basically depends on the square of the electric field. So switching itself is independent on the field polarity that you have just seen. Okay, now if the liquid crystal is biased with a net DC voltage for too long, what can happen that ions within the material get swept toward the polyimide alignment layer interface, and these accumulated ions can form thin charged layer that electrically shields the applied voltage from the liquid crystal bulk. So as a consequence, what you will see, the actual grayscale voltage that is seen by the liquid crystal will be sometimes get misinterpreted. So in that case your image quality will degrade, so you will start seeing image sticking or some after images. So what is the mitigation for this problem? So instead of giving a DC pulse, you basically alternate the polarity of the DC pulse every frame, which is just demonstrated there, and use a high resistivity liquid crystal mixture, which will basically slow down the ion migration. So towards multiplexibility, so that means the ability to independently address many pixels, okay, in a high resolution or high information content display. Okay, that particular approach is called multiplexibility. Okay, and that can be achieved in 3 ways. First, you can develop liquid crystal materials with a steep voltage transmittance curve, so that basically pushes passive matrix NMAX higher, but it's still fundamentally limited. Second will be to use the active matrices that we have discussed today, where each pixel's voltage is controlled independently via its own TFT, and this is the dominant modern solution. And the third one is to develop bistable liquid crystals which do not need continuous active addressing at all. Okay, so that is what we'll be seeing next. Okay, so introducing surface stabilized ferroelectric liquid crystals or SSFLCs. These have two stable orientational states at zero applied field, and each state persists without power once it is written. So this kind of thing can basically help you towards the ability to independently address many pixels in a high information content display. So this topic will be discussed later on, which is beyond today's lecture's content. So with that we conclude today's discussion. So if you have got any query regarding this, you can drop an email to my email address dev.sikdar@iitg.ac.in, mentioning the course name and the lecture number on the subject line. Thank you.